This discussion will talk about concavity of curves and using the second derivative to discover or determine the concavity of curves. Looking here, we see function f of x. We're going to try to sketch its derivative. Now, to sketch the derivative, we want to try to imagine the tangent lines, the lines tangent to f of x. We'll start by trying to find lines that are horizontal. Like, for instance, we can imagine that the tangent at A and the tangent at B would both be horizontal lines. That means that their slope is 0. If the slope of the tangent at A is 0, then the derivative at A has a 0 value. If the slope of the tangent at B is 0, then the derivative has a 0 value. Now we'll try to imagine all the lines that are tangent between A and B. We see a tangent there, tangent there, tangent there. We notice that they're all going to have positive slopes. That means that the derivative would be positive between A and B. But we see that all of the tangents to the left of A, if we try to imagine tangents to the left of A or to the right of B, we see that they would have negative slopes. This tangent here would be a negative slope, this tangent would be a negative. So we see that the derivative is negative to the left of A and to the right of B. Now we're going to get, so we have a sketch here of the first derivative of f. We're now going to try to sketch the second derivative of f. The second derivative of f is the derivative of the first derivative. So now we're going to be imagining tangents on f prime. And we can see a horizontal tangent right here at 0. So we see that the second derivative would be 0 at 0. And we see that before 0, for all the negative values, all the negative x values, the tangents would be positive. So we see any tangent to the left of 0 on the derivative would be positive. Thus, the second derivative is positive until then. And any tangents to the right of 0 would have a positive slope, therefore, a negative slope, that line's negative. So the second derivative would be negative after 0. So the second derivative might look something like this. Now, we need to be able to see all three curves at once. Alright. And what we want to notice that where the second derivative is positive, from negative infinity to 0, the first function, the original function, is concave up. It's like a smiling face. We call that type of shape concavity up, upward concavity. So it's concave up from negative infinity to 0. But from 0 to infinity, it looks as if it's frowning. It's downward concavity. So wherever the second derivative is negative, notice the second derivative is negative along that interval 0 to infinity. So wherever the second derivative is negative, it seems like the function is concave down. And in fact, this illustrates what we will deal with more in class, but this is just an illustration of the concavity theorem. So, here's the concavity theorem. You will want to have this memorized. You will use it frequently, and you want to make sure you get this memorized. You should be able to state it. Just write it out, like the Pledge of Allegiance. Okay. Concavity theorem says that if the second derivative is positive, this is code for positive because numbers greater than 0 are positive. If the second derivative is positive over some interval, then the function f is concave up over that interval. If f double prime, the second derivative of f, is less than 0, in other words, is negative, if the second derivative is negative over some interval, then the function f is concave down over that interval. We will also mention before we close the definition of inflection. Inflection occurs at the point where a function changes concavity. So it's a point on the graph, it's an inflection, we call it an inflection point. It's a point on the graph where the graph changes from one type of concavity to another. So in the example, in the illustration that we just got through using, let's look at f of x and see if we can identify the point of inflection. The point of inflection on f of x is where it changes from concave up to concave down. So it looks like 0, 0 on this graph. And that corresponds, by the way, happens to correspond in this illustration. It's not always going to work out this way, but it happens to correspond to where the second derivative was 0. Notice that the second derivative was 0 when x is 0. So the inflection point does occur when x is 0 on our original curve. So the roots of the second derivative will sometimes, not always, it does in this illustration, but not always, will sometimes correspond to where an inflection is going to occur on f of x.